Hello, everybody. So, what we're doing is we're going to move on to continuity. And then after continuity, we're going to look at average rates of change, and then we're going to have our big unit test over limits. Yay! I bet we're all excited. So, here we go. We're going to jump right into this. So, this is what we're going to be looking at through this whole entire section here. We're going to understand the concept of continuity. We're going to apply the continuity properties, and then we're going to use IVT, the intermediate value theorem. And when I get to that, we'll talk more about that. Okay. So let's start with what is continuity. So continuity is basically being continuous. In the past, we've had graphs that have holes in them. We've had breaks. We have other irregularities. And what we're going to do is we're actually going to look at how continuity and limits relate to each other. So the definition or the look at continuous versus non-continuous. So if we look here at this top graph up here, we will notice that this graph, it goes on and on and on. It has no breaks in it at all whatsoever. And so since there's no breaks and since there's no asymptotes, we are continuous on this graph. Whereas on the bottom one down here, we start at a point and then we jump up and we run and then we jump up and we run and we jump up and we run. This graph as a whole is non-continuous. However, even in a non-continuous graph, we can actually be continuous, because if I asked you to look at where x equals 20, and ask you, am I continuous right here at x equals 20? Your answer is going to be yes, because I'm going to be approaching the same number from both the left and right sides, and I'm going to be defined at 20. So therefore, when I'm looking at 20 as a whole, then I'm actually going to wind up being continuous. Okay? So just because a graph as a whole is non-continuous doesn't necessarily mean that the whole entire function could be not continuous. When we talk about continuity, especially when we talk about limits, we're going to look at primarily these three graphs. On the first one, if we take a look at this, we can obviously see that this graph here is not continuous because there's this big hole here. However, you do have a limit that exists, okay? So your limit exists on this one. If I look at the second one, obviously I'm not continuous because of this right here. Because there is an absolute break and my limit is a D and E, then I'm obviously not continuous either. Okay. On the third one, so this one brings back what we did on the first one. So I do have a limit that exists and I do have a point that's defined, but my defined point is not where my limit exists at. So I need my limit does not equal my f of a value. So we are not continuous here either. So on the first one, my limit exists, but f of a is not defined. On the second one, my limit does not exist because I'm approaching two different values, so therefore I'm not continuous. And on the third one, I do have a limit. I am defined, but neither one of them equal each other, so therefore that's why this graph is not not continuous. So, in terms of looking at the definition of continuity, in order for you to be continuous, this piece right here has to happen. The limit as x approaches a of f of x has to equal that specific defined value. So if my limit at a does not match my defined point at a, I am not continuous at that point. So here are the actual three things here. So there's the first one. Number one, the limit, in this case c, as f of x, the limit as x approaches c of f of x exists. That's the first thing. The second thing, f of c exist. So both 1 and 2 have to exist before you can even contemplate the fact, am I continuous or not? So that's where the third one comes in, because if 1 and 2 are both, if they both exist and they both are the same values, then number 3 is going to be a true statement, because that means you can set 1 equal to 2 and wind up with a continuous point or a continuous value on that specific function. So a function of f is continuous on the open interval if it is continuous at each point on the interval. So that's basically saying there's no holes or breaks or asymptotes or anything else on the interval from A to V, from A to B, not V. If a function is not continuous, it is called discontinuous. So if a function is not continuous, it's called discontinuous. So discontinuity. And we talked a little bit about this beforehand. There are your 3 main types of discontinuity. So let's quickly review those 3 main types of discontinuity. So number 1, you have what's called a removable discontinuity. Removable discontinuity is oh my gosh. It is a Sunday, guys. So this is your hole. Basically, I've got something that looks like this, and then I get to a point, I have a hole, and my graph keeps on going. So I've got something that kind of looks like that. Number 2, I have a jump discontinuity. This primarily happens in absolute value and in piecewise functions. So if you're looking at a graph and it is an absolute value or a piecewise function, then you are more than likely going to have a discontinuity. So you have something that looks a little like that. Okay. You're jumping from one point to the other. Now, the key about the jump discontinuity is just because you have an absolute value or a piecewise function, that doesn't necessarily mean it's not continuous, because these 2 points right here, this point here and that point there, they can actually wind up being on top of each other. So you can actually take this top point here and it can actually start at that same value depending on what your function is. So just because it's either an absolute value or a piecewise does not necessarily mean that it's going to wind up being a jump discontinuity. So you always have to check your endpoints or whatever your restriction values on that to find out and see if you actually have a jump discontinuity there. Okay. All right. The third one. Everybody should know what the third one is. So the third one is your infinite discontinuity. Infinite. Okay. That is your asymptotes. That is your wall that you cannot run up. So you've got a graph that's coming in and doing something like this. And then we'll come out around and do something like this. And you've got this asymptote right here that is running along. Okay. So these are your 3 types of discontinuity. You do need to know these types of discontinuity when you do the problems. Primarily, you'll be dealing with 1 and 3. Again, you'll be dealing with number 2 if there's an absolute value or piecewise. And remember, number 2 doesn't always necessarily mean because you have an absolute value or piecewise that it's going to be discontinuous. So you have to check your points. So let's take a look at this. I want to know, I have a graph. F of x equals x minus 1. I want to know, am I continuous at x equals 2? So I'm looking at the graph. I've graphed it on my calculator. Yeah, it looks like it. But how do I prove it? Because remember, sometimes your calculators will lie to you. Because remember the other day when I showed you We graphed that one function where it had a hole in it, but when you graphed it and you looked at it on a 10 by 10, it didn't look like there was a hole there. But when you zoomed in and then you reran your graph, you saw that there was an actual hole there. So you need to not always rely on your graphs here because you really don't know what's going on right there at that value that we're looking at. So what I want to do is I want to apply our continuity test. So the first thing I want to do is I want to come over here and say, okay, does my limit exist? Well, the answer is yes, because I'm approaching the same value from both sides on this equation. So then number 2, am I defined at that value? So when I plug in my 2, do I get a value back? The answer is yes, I do. The answer is 1. So then number 3 says, all right, well, does my limit and my defined point, do they equal each other? The answer is yes. And so since this is a yes on this one here and on this one here, and this one here matches, then yes, you are continuous. Okay. This is called your continuity test. You always need to check to make sure that you are continuous at that specific point. Okay. Let's try it again. So if I've got this piece here and I am graphing this and I want to know, all right, am I continuous at this point? Again, if I throw it into the calculator, I get something that looks like this. But you should know by now, looking at this piece right here, that this x minus 3, when you plug that in, is going to give me a 0. So something is not going to wind up happening. So try the continuity test. I'm going to give you a few moments for that. Take a moment and see how everything is going, and then hit the unpause button and we will check to see if you're right. All right, let's see how you did. If you applied the continuity test, then that is what you should have gotten. So then when you do this, you wind up with oh, that's not gonna work. Plugging it in, you wind up with a -6. And remember, you're like, well, how did I get -6? Because I didn't get that. Well, if you come over here and you do what you're supposed to do, you got x minus 3, x plus 3, all over x plus 3. If you notice that this and this will cancel, so we're looking at the limit as x approaches -3 of x minus 3. So when you plug that in, you get 6 as that answer. When I plug it in, I get a 0 over 0, so I am undefined, and you know that we have a hole here. But again, look at what happens when you graph it. When you graph this, you don't see that hole. So then, when I compare 1 and 2, I notice that they do not equal each other, so therefore that means my function is not continuous at that x equals -3. And so if we look at our graph and we plug this in, just so that we'll be able to recognize and understand that you need to sometimes actually focus in a little bit better, we're going to come over here and say, okay, second y equals fraction. We've got x squared minus 9 all over x plus 3. And then graph. So when I graph it, that's what I'm looking at. And as you can tell, it looks like it's actually, there's no holes or anything. So it's like, well, I don't understand. But if you hit trace, so here's the first way you can try it out. You hit trace and you go in -3. Ooh, that's a huge sign right there that something's wrong. So now let's kind of zoom in on that. So we're going to change our window. So we're looking at -3. So I'm going to go -4 to -2. And we're going to kind of look at just that area there and watch what happens when you do that. So there's that. Ooh, if you see that, that's really kind of hard to see. So let's kind of zoom it in a little bit more. And we'll go -3.5. And we'll do -2.5. And, oh, where'd it go? Did I make something wrong? Let's see. X min, X max? Oh, I said 3.2, didn't I? 3.5. Let's try that again. Boop. There it is. See, now you can see your hole a little bit better. So it's just that whole being of playing around with these windows. Sometimes if you need to be able to see it a little bit easier, if you need to change your range a little bit and make it a little bit easier, sometimes that'll work. See, that didn't work at all. Oh, that's because I did the wrong Y-min. We want to keep that at -10, and we'll change that to -5. So see, that's why I'm saying you're playing around with your calculator. See, now you can get that little bit break a little bit easier there. So, all right. So hopefully that helps you out a little bit better, and so you can see what's happening. So let's continue on. So I'm going to give you another one for you to try on your own. So you've got the f of x is equal to the absolute value of x over x. And we want to take a look at it at x equals 0 and at x equals 1. So I'm going to look at two different ones on this one, okay? So again, hit the pause button, take a moment, try both of these, and let's see what we come up with, okay? So hit your pause button now. All right, welcome back. So hopefully you tried it, you did it and everything, and let's see what we come up with. So just by looking at the graph, you should notice that by looking at the graph, you should wind up at a 0 that you should be discontinuous, and then at 1 you should be continuous. But let's check to verify. So if you go through the continuity test for the 0, you'll notice that you do not exist on the first one. You're undefined on the second one, and so therefore, since they don't equal each other, then you wind up being not continuous. And then when you do the 1, you'll find out that it matches on 1, it matches on 2, so therefore you are continuous at 1. So that is pretty much, when you're looking at continuity, that is what we're looking for. We're looking for you to go in there and do that continuity test just to be able to verify. So not too hard, not too difficult. So that should be something relatively easy for you to be able to do. So with that being said, let's move on to properties. All right, continuity properties. So of course there's going to be properties. There's properties for everything. The good news is that there's a lot of this stuff that you already know how to do. So this is not going to be hopefully that big of a deal. And a lot of these properties you already know. So let's talk about continuity properties. If two functions are continuous on the same interval, then their sum, difference, product, and quotient are continuous on the same interval, except for any values that make a denominator, primarily going to be on that quotient piece, equal to 0. So that's one of the things you need to remember. So all of them are continuous, except if you wind up with something on the quotient one that forces your denominator to equal 0. So that's the main one that we have to be careful of. So it's just going to be that quotient one. So when we go through all this and you're doing these, when you get to the quotient, just check to make sure that that function on the bottom does not equal 0 for any reason. So you can actually see the properties that we're talking about. Here you go. So you've got your adding, your subtracting, your multiplying, and your quotient. This one here is called a scalar. So basically, I'm just taking a number and multiplying it by my function. So obviously, that's also going to be continuous. And then this one here is my exponential one. That one's also going to be continuous as well, as long as your n is going to be greater than 1. So that's going to be the key for this one. Your n has to be greater than 1. actually greater than or equal to. As long as it's not a fraction, that means you don't have a root, then you should be fine. And then if you have a negative number, that means that you have something in the denominator, which then you have that potential to actually wind up, having a discontinuity in there. But we want to make sure that anytime you're using f here, that your n is going to be greater than 1. All right, so let's take a look at some examples of continuous functions. So these are just examples, so that way when you're looking at them, you should know when you look at these that there's not much that you need to do at all. So you just look at them, answer the question, and go, because you're going to be continuous, because all these has a domain from negative infinity to positive infinity. So when you go through this, take a look at each one of these and do it. You have a constant function where x is continuous for all of x. So basically, that's just your normal straight y equals x line. You have, hold on just a second.